Good morning, good evening, good afternoon, everyone that's attending from different parts of the world. Like Yijun mentioned, we will be talking about using simulation to help enable autonomous driving, which in this case will also include any type of ADAS functionality that's being deployed on the ground and in the world today. So let's start with a brief survey that was recently conducted, I believe, by McKinsey. And what you see here is one of the top challenges for a lot of uh, people in the industry is testing AI-driven systems in real-world driving conditions is very, very difficult because it could potentially be unsafe and also fairly unpredictable and very difficult to get repeatability as well. And what you also see in terms of the sensor development is the fact that when you have multiple sensors, how difficult it is to get these complex sensor combinations validated and tested. And some of the other interesting ones that you see on here is also the challenges in the data interface standardization. So I will talk briefly about standardization as well, and as well as the fact that integration itself is a challenge. So let's move on to see how MSC is addressing this challenge. So before we proceed any further, I just want to talk briefly about um, the the bigger entity called Hexagon that MSC software is part of, and how we're all getting connected together within the Hexagon portfolio. So in the geospatial or in the positioning intelligence division, we have autonomous stuff that provides a research platform for vehicles by combining various sensors and providing you a prototype vehicle from which you can start on which you can start deploying your ADAS or self-driving algorithms to see how well it functions. We also have Novotel that provides precision GNSS units for getting centimeter level GPS accuracy. With Hexagon Geosystems, we work closely with Leica Geosystems within there to help do the mapping of the road in a fast and efficient way. I'll come to that when we're talking a little bit more about how we're connecting it to our simulation solution. And on the MSC software side, we have Adams and Adams Real-Time, which is our state-of-the-art vehicle dynamics simulation code and used by almost all the OEMs worldwide today, as well as our data management, machine learning, and AI group that's looking into efficiently developing scenarios and other data to be generated for validation of autonomy functions as well as data functions. The core of what I will be talking about today, though, is virtual test drive (VTD) that you see here in the center block, and we will briefly discuss the ability to deploy different driver models, traffic sensors, and building out a 3D environment to be able to validate a lot of the functions we've shown in the survey earlier. So moving on, a brief history of Virus as a company. It was started by Marius Dupuy and has been around for about 20 plus years, in which time we've not only developed the virtual test drive product, but also been a key partner in standardization initiatives, OpenCRG, OpenDrive, and OpenScenario. Now, just to briefly mention uh, about each of these open standards, OpenDrive is how we describe the road networks. So the lanes, the merges, the different types of lane markings, the traffic signs, and all of that go into the definition of an OpenDrive data format file. And when we mean again by standardization initiatives and the fact that these are open means that the specifications are available online. You can see the website links at the bottom, and you can anybody can create data in this format because the specifications are available. OpenCRG is a way to describe the road surface roughness. If you have potholes or speed bumps or a cobblestone road, you can use OpenCRG to describe those surface level properties. And Open Scenario is a relatively newer standard that we've been co-developing with multiple OEMs and suppliers to help define what are called scenarios or maneuvers or events, as you want to call it, whether it's a lane change, whether it's a blind left turn, whether it's a highway merge or a highway exit, so on and so forth. And the apart from that, VRES has also been with our virtual test drive products. We've also been part of a couple of key research projects in Europe. The Pegasus project in Germany that was originally focused on trying to find ways of certifying and proving out highway autopilot type functionality, and enable S3, which is a Europe-wide automation project. And VTD is the only simulation tool provider in this consortium. There are also in the US, we're part of with SAE and GM, we're part of the Auto Drive Challenge, where 8 universities have been chosen to develop autonomy functions for a given vehicle, and we work closely with the universities to provide them with simulation software tools. So the key thing, before we proceed any further, one of the key things to mention here is that in any given process, when you're trying to move from simulation to a verification and validation process, or to a testing process, a key aspect here is to look at how VTD can move from software in the loop or model in the loop to either driver or vehicle in the loop, or driver in the loop, or hardware in the loop. And this kind of seamless ability to move between different types of environments gives our tool a lot of flexibility. And here, if you look through each of these little sections, you can see here that anything that's marked out in blue is basically running in real time or is a real component. And then the other ones in green are virtual components. So for example, in a vehicle in the loop situation, you could have virtual sensors and real sensors kind of combined. You could have virtual and real traffic that could also be combined. With hardware in the loop sometimes as well, you can have a virtual ECU plus real sensors combined as well. So the fact that we can move between a lot of these functions fairly easily provides us with a lot of freedom to and flexibility, which is what our customers prefer. Going the next step into how virtual test drive works. This is a one-slide summary of the workflow itself, and I will go into each of these sections in more detail as we continue through this presentation. The first step when you're trying to design or work on an autonomous or an ADAS function is to create or build out a 3D environment. Now, there is a way to build out the static. There are multiple ways to build out the static content, which I will describe in the next few slides. The idea here is that you would generate a 3D environment with your open drive files to define the road networks. You'd have graphics to define the road furniture like buildings and trees and signposts and whatnot. And then if you want to define the road surface layer itself, you can add the OpenCRG road file format data on top to define road surface friction or potholes and speed bumps, etc. Once the 3D environment is defined, the next step is to go into the dynamic aspect of it. So think about the 3D world as a static aspect, and the dynamic aspect is all the traffic elements, whether you have your subject vehicle, multiple other vehicles, traffic lights themselves, the behavior of the traffic lights, anything that can contribute to fundamentally creating a maneuver or a scenario would be done through our scenario editing tool. Again, there will be more details about this in later slides. And once you've set up your traffic, once you've set up your maneuvers, then you run the simulation. This is a small screenshot of the VTD interface. And as soon as you run the simulation, you will have real-time animation, and you can take into account vehicle dynamics and multiple fidelities. and also have realistic traffic as well. So this is just a the basic setup of running a scenario, setting up the 3D world and running a scenario in VTD. The next step really comes down to the usage of sensors, the perception aspect. Now, there are two ways in which we address perception within our tool. One is the simplified object list-based sensor, where we're capturing ground truth data for each object, either on the road itself from an open drive database or the dynamic traffic elements. Apart from that, we can go into detailed perception models where if you were doing specific camera perception studies for either software or hardware in the loop, and if you want to do LiDAR simulation, we have the ability to do ray tracing in real time to account for detailed LiDAR models as well. We also provide the ability to connect with tools like MATLAB Simulink. We're compliant with the ADTF protocol and have the ability to deploy on ROS as well. So co-simulation and working with a lot of third-party tools not is not new to us, and we've been doing this for a long time now. Okay, going on to the next slide. So here's a brief, once you have this workflow put together, I just wanted to, before I dive too much into the detail, I just wanted to show you a brief look at the animation itself of how VTD looks. Here, what we're doing is we have something called physically based rendering. Again, something I'll talk about in more detail. Allows you to do vary different times of the day. The shadows that we project are fairly accurate, and we're also able to take a lot of detailed material properties into account when we're doing this kind of animation here. So this is the advantage of using something that is fairly photorealistic in terms of its rendering as well. Weather conditions like rain, the road wetness, the road surface friction, all of these things can be taken into account as well. So the first thing, which is building out 3D environments. Now, there are two different approaches to build out 3D environments. I believe my colleague Luca had presented briefly on this on his webinar, which was a couple of months ago or a month ago. But the basic idea here is that you can either use a measurement-based workflow or a modeling-based workflow. Now, I'll talk briefly about the modeling-based workflow, which means that you have no dependence on any type of measurements, and you can parameterize it. And the way we approach this with our tools is that we provide customers with pre-built tiles for different countries, whether it's China, the US, Japan, etc. And you can use these tiles, think of them as Lego blocks, and you can connect them together to form a road network that includes, let's say, a highway exit or an urban road with all the necessary traffic signs and buildings included. Now, that's a generic representation of an environment. You can also use our tool to do something that's very geo-specific. We've done things like the 6-level highway intersection in Shanghai, and this can be done purely from a modeling aspect, but the accuracy is obviously not as good as what you would get out of doing a measurement-based workflow. When we go to a measurement-based workflow, we have been working with our partners at Leica Geosystems and they have this unit called the Pegasus 2 that has multiple built-in cameras, a LiDAR sensor, precision GPS unit from Novatel, and is mountable on the roof rack of a vehicle. And you're able to get 360-degree imagery from this. So the key aspect is that you can drive close to highway speeds at up to 100 kilometers an hour and are able to scan the roads and then extract the data, use the software that Leica has built out to convert a lot of this data into the Open Drive file format and then export that into VTD. So today we're focused mostly on getting the road information, the lane information, anything that pertains to Open Drive. We're working on an OpenCRG extractor as well to be able to get the road surface information. And a longer term, we will be able to extract the building textures and formats as well. So once the 3D environment is built out through this measurement-based approach, the next step is to create a scenario. Now there we have a tool within VTD, that's our scenario editor. One of the key things I want to mention here is that we support Open Scenario today, and as the Open Scenario standard continues to evolve, we will continue supporting it with our tool. And we have the ability here to inject not only single types or single elements of traffic, but also bulk traffic as needed within this inner and outer radius. You can specify different types of maneuvers here for the vehicles. We can also do traffic light facing and traffic light behavior. And we have various trigger options based on time to collision or pivoting about a certain vehicle. Apart from that, we have the ability to use something called SCP, which is our command language, which is XML based, to inject various commands either when the scenario is running or pre-scripted before you run the scenario. And we can run up to 200 plus concurrent vehicles within a scenario in real time, which is fairly significant given the amount of compute power that takes. The second part about the scenario editing and the graphics is that with each of these vehicles, either um, you can either have what we call autonomous or deterministic behavior, which is I could set up a vehicle and just let it follow the rules of the road, maintain the speed limits, follow all the traffic signs, and it will drive around very safely and try its best to avoid any type of collisions or accidents. The other thing we could also do on the other extreme is to give a vehicle a certain speed and a certain path, or any one of these, and then just have it do that and ignore everything else that's going on in the road. You can have it go into the opposing lane. You can do all of those kinds of things within VTD. We also do have the ability to provide realistic traffic density and features in here. And what you see here in this flow chart, which is important, is that we can inject any type of ADAS function, or you can have a human driver in the loop, or you can inject any type of custom AI driver model, or use the VTD internal driver model, and control both the lateral and longitudinal dynamics separately if you want from a vehicle dynamics perspective. With VTD, we are able to integrate any third-party vehicle dynamics as needed, but we also have our own. VTD has two different levels of vehicle dynamics built into it, and then we've also integrated, like I had mentioned very early here, we've integrated our Adams real time, which is our highest fidelity vehicle dynamics model to date available within VTD to be able to do high fidelity ride comfort or more detailed limit handling simulations that current parametric models will not be able to handle. We can also do traffic flow simulation or inject data from external traffic flow simulation through Sumo, and in the longer run with PTV, Vison, etc. And VTD is open enough to be able to accommodate these types of third-party entities. And here you can see on the right, we have a pedestrian, we have a horse and a rider on a horse. This also shows the flexibility in terms of how we can inject any type of 3D model or external entity within VTD. So for different types of scenarios where you have edge cases, where you typically not seen your normal entities, you can inject different third-party entities in there as well. We also have our own pedestrian simulation models that we are currently using within VTD. Here's some examples of some scenarios that we created or worked on as part of the Pegasus project. This was for highway autopilot certification. As you can see here, whether it's a double lane change or two lane changes with an emergency brake, having an emergency vehicle go, we've been able to account for all of those within VTD. So we do have the ability to create various types of scenarios and run them within VTD. Apart from that, we do provide customers with Bureau NCAP scenarios that there are about 16 or 20 currently that we provide customers with for them to be able to do any type of zero cap scenario simulations. And apart from that, we have a bunch of other example scenarios running within VTD as well. So going from the execution of the scenario to being able to run it, the next step is, like I had mentioned in that workflow slide, is sensor modeling and doing perception studies. So now there are two ways to address this perception aspect. One is doing the post sensor fusion object list based perception, which is mostly used for motion planning and control. And on this side, what we're working on is purely, and there is the other side, which is the perception aspect of it itself, which is dealing with camera models or with LiDAR models to do actual perception work. So as you can see here, we're able to take into account different weather conditions, different times of the day through our physically based rendering approach, which means that we apply detailed materials and textures per per element in VTD and are able to get different returns of light for doing very accurate sensor modeling. We also have the ability to do headlight simulation, headlight intensity simulations, taking into account again different weather conditions, different reflections, and all of those kinds of things, whether it's wet or dry, being able to take all of that into account. And when it comes to camera modeling itself, within VTD, we have the ability to do distortion, blending, chromatic aberration studies. We also have a lens configuration tool that allows you to calibrate your virtual lens to the real lens that you're using and create custom lens types like the fisheye camera that you see here on the screen as well. Given the fact that you can do a lot of this in software in the loop, the next natural progression to this is a hardware in the loop approach, where you can put the camera itself that you're using for your automotive application in front of a screen and have VTD run the simulation in front and see how well the camera is able to detect objects. The workflow looks something like this, where you have the scenario itself that's being run with some traffic simulation. You have your vehicle dynamics in here, and then the image generation goes into a screen then the camera perceives, and then the driving function, if you have any, can be deployed directly within VTD, and then you can see how the whole system works together. It's a closed loop operation, and the fact that it runs in real time. The other approach that we can also use here is that if we could use a video interface box that would replicate the imager, and you can bypass the camera lens and feed data directly into the camera ECU. And this would really work well in low contrast situations where the monitor might not be able to capture that image for the camera to perceive well enough. So given that fact, moving on from not just cameras, we also have the ability to take into account LiDAR simulations, and we do a physics-based LiDAR point cloud generation where we calculate the intensity of these point clouds based off of the distance from the subject vehicle, and we color code all the different points. And here, what you can see is that when the light hits this vehicle, it doesn't just pass through it. And so there is this empty zone here. So we're trying to be very, very physically accurate in terms of how we calculate the LiDAR hit points and the returns within VTD. Again, this type of point cloud simulation runs today in real time using an NVIDIA GeForce GTX GPU as well. We also, with the use of NVIDIA's optics ray tracing capabilities, we are also able to do real-time ray tracing here, as you can see. And in this example, we've color-coded the environment into red, green, and blue, where red is the direct hit of light, green is the first reflection, and blue is the second reflection. So as you can see here, if the wall is rough, the light does scatter and disperse, and we're able to take those things into account when we are running this simulation in VTD. Apart from that, not only when you have different types of surfaces, when you have a clean versus a dirty surface, you'll see that there is a difference in the surface reflection as well. And when you go between dry and wet, again, you see a big difference between how much of that green light increases versus the red because you're seeing more of the reflected light. So we're again able to take a lot of this into account with VTD by using the ray tracing engine and being able to run this in real time. So this is really, really important for a lot of the LiDAR simulation work that people are doing on the perception side. So going into the post-perception aspect a little bit here, and briefly staying on the perception part of it, we can also do color coding of objects. So if you're doing semantic segmentation studies, we have the ability to color code all the different objects in the environment, and you can use this to do semantic segmentation studies in VTD. And then, as I had briefly mentioned, we also do the post-perception, the ideal sensor or an object-list-based sensor, where we put bounding boxes on each of these different objects and then are able to derive the ground truth information for each of these objects. Now, if objects are partially or fully occluded, we are also able to take that into account by not only measuring the distance from the subject vehicle, but also measuring the occlusion through an occlusion matrix and calculating what that occlusion matrix is and presenting back to the user when the simulation is running. So you get an account of both partially and fully occluded objects for each of these object-list-based sensors. Also, the fact that now we have the ability, since VREF and MSC are now all part of the same company, we've been working together to closely integrate our high-fidelity Adams car vehicle dynamics models with VTD. Just a brief mention of what Adams is. Adams is our multi-body dynamics solution that has been around for over 40 plus years and is one of the most trusted vehicle dynamics software tools in the world, and the highest fidelity vehicle dynamics software tool that's available in the market today. And what we're able to do is connect Adams to VTD to be able to run our simulations as a co-simulation or as an FMU. And the advantage here is that you can go both ways, where you can run Adams in real time to take into account limit vehicle dynamics that has enough nonlinear behavior that the simple vehicle dynamics or parametric vehicle dynamics models don't take into account. And the second thing you can do with VTD here is that you can have VTD run slower than real time so that you can do higher fidelity vehicle dynamics or higher fidelity vehicle modeling aspects like ride comfort or durability type studies within Adams. So the 3D environment and the sensors can come from VTD, and then based off of the perception, the vehicle behavior, and the vehicle analysis can come from Adams. Which brings us to the next point of the fact that we can take VTD and run it on driving simulators, whether it's a static platform or a dynamic platform. We're able to take that into account. In this case, as you can see here with this semicircular screen, we're able to take multiple images and blend them into one through our ability that we have within VTD to stitch multiple images together, or being able to generate multiple images from multiple computers. This is an example here of a user actually driving an Adams model within the VTD environment. So the steering, throttle, and brake information is going into an Adams model. The vehicle dynamics is being computed in Adams, and then the response is being displayed out here in VTD. So the fact that we can now run and have a driver in Adams, drive an Adams model in a 3D world means that you can now do higher frequency analyses like ride comfort with a combination of VTD and Adams. Again, this is what the workflow looks like for a driving simulator type approach. You can have multiple image generators, and you can combine these channels so that the viewer feels that they are looking at a single image, or they feel like they are driving in an actual environment. And you can either choose to use Adams real time or any other vehicle dynamics engine here. And the controls for steering, brake, and throttle in this case comes directly from the human being. So moving on from the different types of applications to a more fundamental question of what we've talked about is how do you enable a safe autonomy and safe testing, one of the biggest challenges is the fact that the number of interesting miles that need to be driven and the number of scenarios that need to be tested or validated are in are significantly large. So our team has focused on being able to generate a test automation tool, also, but at the same time being able to do an efficient sampling and generation of scenarios that would be fundamental to testing specific ADAS or autonomy functions, and try their best to really find the edge cases to see how well the algorithm performs. And this apart from that, what we are also providing is the ability to do automatic post-processing through our data analytics and AI-based, rule-based classification, and provide you with interfaces like this from Tableau or with whatever tool that the customer wants to use to verify and validate their AI algorithms and predict the performance and quantify the safety as well. And this basically allows customers to go from model in the loop to software in the loop to hardware in the loop in a very seamless and smooth way. As you go from model or software in the loop to hardware in the loop, the number of tests that you need to run have to be funneled down or have to be reduced because HIL testing is a lot more challenging and a lot more expensive than software in the loop testing. So what we provide customers is the ability to suss out the most important scenarios that they need to run and score the relevance for each of the simulations that they're running, and then move that on to the next stage, which is hardware in the loop. So that's the aim with our tool, our VTD Scale tool. And here we just have an example of being able to run thousands of simulations in parallel with VTD. As you can see, we could vary the static environment, we can change the error injection, and we can change any of the dynamic scenario parameters as well. So this allows us to create a very, very robust set of scenarios that could really push VTD, push the algorithms to the edge, and generate a lot of productive value out of what we can do with VTD today once you scale it up to hundreds of thousands of scenarios. So that was my presentation for today. Thanks a lot for listening.